when determining language, it's really easy.
Okay, let's try this again. So, real quickly, I'll post through this just because it appears as if I apparently didn't push the power or the record button. So, the warm-up is simply to go through and find the perpendicular vector to 6, 2, 3, 1, negative 3, 0. We did so by finding the cross product. When we found the cross product, we used a determinant to set this up in terms of minors. There's a slight question right now as to whether this is positive or negative. I'm going to check that tonight and find out. The answer that we ended up getting today is, or the perpendicular vector then would be 9, negative 3, negative 12, or negative 20. And I will go through and verify the cross product this evening just to make sure. But if so, the only difference we would see is that this would be a positive instead of a negative, just changing the direction on that second component. So I'll get that fixed. If you guys can keep an eye on that camera, make sure that thing keeps on blinking, because I'll forget if I allow myself to. So okay, so anyhow, I'll follow up on that and find out for sure. So what are we going to use this for primarily? First off, it's mostly just to kind of build some understanding. But if we need to go through and define say a z-axis given a plane, then we can go through and use this to determine that perpendicular axis from the plane that more likely we're going to associate with our x and y.
Does this go through the origin necessarily, or?
Each of these vectors probably are going to be, well, they are going to be referenced to some origin, right? And more than likely to the origin of the frame that we're trying to define. That makes sense? Okay, because virtually everything that we're going to be interested in is either defining vectors that represent a position or that represent a rotation. Everything else in our world really doesn't matter. It's just all about rotations and displacements. Good? Okay, so let's buzz on then. That cost me a little bit of time, but we'll get moving on through. So yesterday we just got started talking about, so it's muffin day at Weininger's, so not only have I had 3 cups of coffee, but I'm buzzing on the muffin high right now. So. Yeah. Okay. So yesterday we started talking about translations, and one way of defining a translation, by the way, a translation is nothing more than a displacement from one frame, or well, displacement. I'll just leave it at that. So what we can do is we can define a position factor that describes a translation from one frame to another. So if we have a displacement in frame, say A, what we can do is we can say that the position vector representing that displacement is in frame A. And this is typically read as P vector is described in frame A. Okay. Another thing we can do is we can use this position vector or this displacement vector to point to another frame. For example, if we wanted to go through and say that the P vector is described in frame A and points at the origin of frame B, then what we do is we use this type of notation. And this is kind of cumbersome because it takes quite a while. I will say that this seems to be relatively isolated with this particular author. However, this particular author is used in many robotics courses. So while I haven't seen other authors use this notation, just with as prevalent as Craig is in robotics classes, you'll run into it inevitably if you do anything more with robotics. So, okay, so with this then, we can go through and define two frames. We can define frame A, and then from frame A we can use a position vector to indicate the displacement from the origin of A to the origin of B. And that's really kind of cool. So let's say that we've got that's a really elevated view of that coordinate system. So I'll flatten it out a little bit. Okay, so we have frame A defined here. And I will go ahead and label my plus Z, plus X, and plus Y. And then let's say that over here we want to define a frame B. This frame doesn't have any rotation or anything else in it other than a displacement from A. So all we would have to do is describe the direction, the position vector that is displacing frame B from frame A. And this position vector would look something like that. Now, what two things could that position vector represent in our robot? Could represent the length of a segment. Okay, or what else? What's that?
The length of a movement.
Length of a movement, okay. We know that we have two types of joints. We have a revolute joint, which is the rotational joint, and we have a prismatic joint, which is our translating joints. For that reason, if we had a prismatic joint that is moving in and out, then we could go through and use this position vector, just change the length of that position vector to model that degree of freedom, okay? So, when we go through and work with these things, in our particular robot, do we have any prismatic joints?
No.
No, but in the old Atlas robots that are in the room next door, we know that in fact one of their primary axes or their primary degree of freedom is a prismatic joint. Have you guys seen those? So I wonder if that's over there now. I'll go ahead and grab one real quick.
Those red ones, yeah, it's the one with the rubber chain.
Up and down and then they can kind
Yeah, so I have some myself.
But I saw your name yesterday when I looked. I thought that it was 11:30 for some reason, so I went up 11:30 and everyone was in there just halfway through the lecture. I was like,
Yep.
oh.
And then I see the name for it sometimes, it's just like,
Yeah.
it happened.
Yeah. But he was
Nothing.
Alrighty, so let me see if the camera is actually,
No.
not really. There we go. So in this case, what we have is a revolute base joint. We have a revolute shoulder joint. But then we have a prismatic arm, okay? This prismatic arm is going to move in and out in order to provide the reach, in order to allow us to grab the different objects. This is a rather unique type of construction. Most robots don't follow this type of configuration. In fact, you'll find there really are few robots that have a prismatic joint outside of the Scarab robots that I talked about early on. Do you guys remember how a Scarab robot was configured?
4
It had 4 degrees of freedom. And
It didn't have that end effector, so that it should roll.
right, it just had a side-to-side angle. So we could position the end effector in X, Y, and Z, but we only provided it 1 degree of freedom in order to control its orientation. So in that case, what we have is a prismatic joint that moves our robot up and down in Z, and then the revolute joints position the end effector in X and Y, which then provides. So we might have our arm configuration like this, and then our end effector is out here on the end, providing the angle that would align it with the wafer cartridge or whatever else we're interested in. So, okay, so with this then, for our purposes, what we're going to be doing is using these translation vectors not to model prismatic joints just because they're not that common. We're going to be using them primarily to describe the length of a segment in our robot. Good? Okay. Now, there's a couple of different things that we can do. For example, if we had a vector described in B, so this vector will be described in B, what might we be interested in doing? And we've already talked about this yesterday. I'm just kind of buzzing back through it to help review this stuff. Is frame B, or would frame B necessarily be considered our universal coordinate system, or relative to our universal coordinate system? Probably not. More than likely, we're going to say that the base frame is associated with that universal coordinate system. This is where we want to have our 0, 0, 0, if at all possible. Okay? Well, that means that this position vector described in B, ideally we want to associate back here with frame A. So how are we going to go through and do that?
Would you just add them together?
Just add them together. This is just vector algebra, right? We're just adding the two displacements together to get the corresponding vector relative to A. So what we can do is we can say that, I'll color code this, the position vector described in A is nothing more than the position vector described in B plus the position vector described in A that points at the origin of B. That makes sense? So in this case, if we have the position vector described in B, and we have the position vector described in A that points at B, then what we can do is kind of think about how the canceling would go on here. We can say that B is on top here, B is on bottom here, they cancel out and leave us something described in A. This is kind of a loose association here. It's kind of like the engineering economics that I'm teaching now. It's like really flaky. I mean, it's a very loose interpretation of algebra, but we'll take it. So, So what we can do here, and part of the reason why this notation has been developed is so that we can see that the B superscript is going to cancel the B subscript, leaving us with something described in A. Good? Okay. Now, what if we wanted to go the other direction? What if we had a vector described in A, and we wanted to describe it in B?
Subtract A B origin.
Yeah, we can just move this over here, right? I mean, this is just algebra at this point. So if we wanted to go through and say that some vector is described in B, and we wanted, or some vector is described in A, and we want to describe it in B, well then we're just going to have the vector described in A minus the position vector pointing from A to B. Now this is kind of an important point here, and you'll see why here in a minute. How could we interpret this minus A, or P, A, and B, or B, or an A? Yeah, that's it. If we're subtracting a vector, we're pointing the other direction. So, let me do this in black, I suppose. What's minus the position vector in A pointing to B? So we could say that this position vector described in A pointing in B is the same as the position vector described in B that's pointing at the origin of A. What's the nice thing about this? We got a bunch of translations that are pointing at some terminal point out there. How do we undo them? We subtract them off. So if we move through a series of translations to get to some terminal point, and we want to work backward through the chain, then we're just going to go through and subtract off each of those translations to get back to the origin. That makes sense? And this is particularly useful to us when we have more than just two frames described in our robot. For example, we would have one translation in the first axis, another translation in the second axis, a third translation here, a fourth translation to the subsequent join, and so on and so forth. Okay, so this becomes very, very important to us as we put these together. When we're working with MATLAB, this is going to result in a fairly efficient algorithm. If we go through and directly add and subtract these vectors from one another, we're not performing any multiplication, we're not performing any, or introducing any extra dimensionality, but I'll tell you that this is going to require a little bit more thought when you write your code. In the example that I put together today, I represented everything in the homogeneous matrices, because then I could extract the information I needed from those homogeneous, transformations in order to get the job done. Okay. Everything is packaged there. Because it's packaged there, I can just extract the data that I need in order to produce the plots that I want. So, okay. So, while we'll probably, while we have the option of working directly with these translation vectors discretely, oftentimes what you see is that these are used to establish what are known as translation transformations. And this is going to be somewhat, I'll just put it up here. Okay, so the T does not stand for translation. It could, in fact, in this case, it makes a lot of sense. But in general, the book uses T to represent a general transformation rather than, in this case, a transformation. Okay? So what this is that we have a translation described in A, or that puts B in terms of A. Okay? So this transformation, we could say relates frame B to frame A. Okay? So it puts everything in frame B in terms of frame A. So when we have a translation here, or a transformation, we're going to go through and package it as I've already said, as a rotation matrix, which we're not worrying about quite yet, a position vector that is described in A and points at the origin of the next frame, that's described in one frame and points to the origin of the next frame, and then a row of zeros and a 1. This is just our 4-dimensional unit vector. Okay? If we're specifically interested in a translation, then this is going to look something like this, where we have an identity in the upper quadrant, not necessarily quadrant, followed by our position vector, and the last row is the same. That guy's going to be kind of hard to remember to work around. So the identity then is just going to be populated with our I, J, and K. And then we're going to have our X component of position vector, the Y component of position vector, and the Z component of the position vector. Okay, and so let's come up with a displacement and see if this actually does the job for us. Provide me a displacement vector here, just whatever you want, and then we're going to come up with a displacement vector, or a vector described in B as well. I'll actually say that the position vector in B, holy cow, right there. I will say that the position vector in B is just 1, 1, 1. I'm writing it as a column vector because I'm almost out of workspace, and we're going to be doing a matrix, a multiplication between a matrix and a vector. What displacement vector do you guys want between frame A and frame B?
571.
571, okay. So that means that if we want to use this, or define a translation vector, transformation from frame A to frame B, we would have 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 5, 7, 1 as our position vector, and that is our translation transformation given the position vector we specified. Now in this case we have, by the way, what would the corresponding unit vector be, or the corresponding vector be if it's described in it? it'd be the vector 571 plus the vector 111, so what is that, 682? So we're expecting an answer of 682. So we're going to multiply this by, and keep in mind that we have to introduce an additional 1 in that vector just to make sure that we have the correct dimensionality. Okay. This has to be a 1, otherwise this entire process doesn't work. Okay. So in this case, what we have is, let's see, 1 times 1 plus 0 plus 0 plus 5 times 1 to give us a 6. And then we have a 0 plus a 1 plus a 0 plus a 7 times 1 to give us 8. Then we have a 0 plus a 0 plus a 1 plus a 1 to give us 2. And then finally 0 plus 0 plus 0 plus 1 to give us 1. That is, in fact, what we were interested in. That makes sense? Now here's something that's kind of cool. What would the inverse be? Well, I'm going to do this even though I promised a couple days ago that I wouldn't, but I'm going to manually calculate the inverse. I probably really should have tried not to erase that, but it's too late now. So I'm going to calculate the inverse of this matrix by creating an augmented matrix and having it equal to the identity. So we have 1, 0, 0, 5, 0, 1, 0, 7, 0, 0, 1, 1, and 0, 0, 0, 0, 1. So it's just a bit big. And then I'm going to put my 4x4 identity on the other side. Okay, what row operations are we going to have to do here? Nothing here, right? This is already the same as this, so the last row is done. Okay? In order to get this set up the way we want it, that is 0, 0, 1, 0, we're going to have to take row 3 minus row 2. I'm sorry, row 3 minus row 4. So we have row 3 minus row 4. Here we have row 2 minus 7 times row 4. And finally, here we have row 1 minus 5 times row 4. And that's all we have to do. If we perform those row operations, then we have the identity on the left-hand side here, don't we? Okay? Well, that's what we end up with. How does that correspond to what we've already talked about? How did we say we went from frame A to frame B? Well, I'm sorry, that I'm asking the wrong question. How did we say we could undo a translation from A to B?
Subtract it off there.
Subtract it off, right? What are we doing here as compared to here? Just moving in the other direction, aren't we? So that means that if we have a translation matrix defined in A, or that describes frame B in terms of frame A, we can come in and define the inverse as being equal to the transformation, or I'm sorry, translation it describes A in terms of B as nothing more than the components that point in the other direction. That means if we work all the way out to the end of our link, but we got lost somewhere and we need to work backwards a little bit, all we have to do is change the signs of those translation vectors in order to move backwards. Good? Okay, so what I'm going to do now is take a look at how I implemented this in MATLAB here. And to do this, I'm going to have to zoom way out. Oops, that's the wrong direction. Should I just make everyone deal with a tilted screen? Good enough. Okay, so I have written a script here, and I'll describe the script as we go through it. But for now, I'm just going to show you what this looks like. In this case, what I have done is define two frames. Both of these frames are translation, are represented by translation transformations, and each of these frames are going to go through and describe the position of each subsequent frame in terms of frame A. Okay. So I'll go ahead and run this, and you can take a look at the result. Okay, so what I have is the black frame here corresponds with our frame A, our base frame, if you will. This base frame has a translation along the green vector to frame B. Frame B then has a translation vector that points to frame C. And you can see that as we rotate this around, sure enough, it is definitely translating the positions from the origin here, which is representing our base frame, out to each subsequent joint on that robot. In this case, we have two joins. Well, we could consider, well, two joints. We don't know anything about those joints. And then this final link would represent the end of that group. Okay, so in order to set this up, what I have had to do is go through and I define an IJK matrix. You'll notice that this is a 1, 2, 3, 4, 5, 6 by 4 matrix. Okay, this is our data matrix. Okay, and what I have done is when we run that, I have my IJK vectors that are just representing my object that I'm moving around in space. Okay. Now, why are there 6 columns here? Well, if you'll notice here, this first row has 0, 1, 0, 0, 0, 0. What do you suppose that first row represents? Our I vector. Okay.
Be your start, your end.
Very good. This is the start x, the end x, the start x, end x, start x, end x. Okay. When we're dealing with our plot 3 command, what we need to do is specify an x vector, a y vector, and a z vector. And each of those vectors have data that corresponds to each other. So this represents the start X, the start Y, and the start Z. This represents the end X, end Y, and end Z. And then this is the start X, start Y, start Y, start Y, and start Z for the next vector, and so on and so forth. Okay? So you can see that there's a bit of typing to get this set up properly, but once we do, it's not going to be a particular, once we get familiar or used to working with this, these instructions, it's not going to be particularly challenging. It's just like anything else. It takes a little bit of time to get familiar with it, and once you are familiar with it, then everything's good. So in MATLAB, when you want to define a row vector, you can use the commas to separate the elements within that row vector, and then to move on to the next row vector, you use a semicolon. This would be our next row vector. This is our next row vector. So this is our X vector, Y vector, Z vector, and then we need our row of ones in order to maintain proper dimensionality. Make sense? Our first transform, I could call this transform from A to B or whatever, but I just called it T sub 1. You can see that our X displacement is 2, our Y displacement is -3, and our Z displacement is +3, and then we have our unit vector to set up dimensionality. Our second transformation is has a X displacement of -4, a Y displacement of 2, and a Z displacement of -6. Good? Now here's something that's really kind of useful. Notice that when I define frame 2, it is nothing more than the first transformation times our data array. Okay, so that's really cool. But how did I define frame 3?
Use both sets of data.
What's that?
Use both sets of data.
I use both sets of data. So we can see that when we're moving from joint to joint through a series of transformations, all we have to do is multiply the matrices together in the proper order in order to render or the absolute transformation from our base joint or from our base frame. And that's very valuable to us because if we go through and if we wanted to, we could lay this guy out flat with specifying nothing more than the length of each of these joints, and then we could say, okay, well, as our theta angle changes, we're going to be moving each of these joints into a different position. That makes sense? Then we had to, had to get a little bit creative. I had to pull the data out of my I, J, and K that I wanted to represent X. So this notation tells me to look at the first row and all of the elements in that row, the second row and all the elements in the row, the third row and all the elements in the row. If you want to specify only a couple of those elements, you could say, well, do something like I, J, K. Oh, this is off the side of this array. Row 1, elements 1 and 2. The only thing you have to be careful of is to make sure that you have an even number of elements that you're specifying, because plot 3 is going to expect an initial point and a terminal point for each of your components. If you have an odd number of elements defined in this array, then you're going to be defining the start, and then the subsequent plot 3 command will initiate with the final position. That makes sense? So it's really easy to go through and define these so that you have an odd number of elements, in which case you don't know where you're ending up. So, okay, so a couple things that you'll have to be mindful of. You're going to want to make sure that you use the hold command because you're going to be plotting multiple vectors. If you do not use the hold command, it's going to clear the screen between each of these plots. Okay. Secondly, while the grid is kind of optional, I did that just to kind of put it in perspective. That way it didn't look like things were floating around in space. The axis, however, for any of you that have used MATLAB, you've probably realized that MATLAB is not the best program in the world at scaling your plot data for you. Sometimes it does a good job, sometimes it does an absolutely horrible job. So for the purposes of this class, I'm going to recommend that you specify the minimum x, the maximum x, minimum y, maximum y, and minimum z, max z. Okay? And that is in a 6-element vector. And most importantly here is specifying your view, your point of view within the 3D environment. This isn't something that you have to do within within a 2D plot. It just automatically assumes that you're 5 units away from the screen. But in 3 dimension, it tends to pay the most limited point of view possible and displays things relative to that point of view. So in this case, what I did was I chose a position 5, 5, 3, and I chose that position so that I was looking at it so that my positive x was on the left, my positive y was on the right, and I was looking in the middle of that field somewhere. And I didn't want it to be looking straight down, otherwise, or at a 45-degree angle to the plane. So I specified a position that was slightly below that so that it gave me what seemed like a slightly better point of view, but you could really define any viewpoint that you want. Good? Okay, so let's play around with this just a little bit. Let's go through and put some stuff in. Oh man, Joe's not here telling me what I need to click and stuff. I miss Joe. Oh. So, here we go. What I'm going to do is, I'm going to go through and, let's see. I'm going to say that our transformations, for x equals 1 or 0 to 4. Oh, I know. And I'm not going to worry too much about describing the syntax here today, but as we run into the run further into the course where we need to specifically know some information about each of these functions and stuff that I'm looking at, I will provide it for you. Today I'm just wanting to kind of give you a brief introduction to this. Okay, so what we can see is that by varying x here, what we have done is move that frame incrementally across the screen. Okay, so and as a result of that, I need to actually put it in a slightly different, that draw now function in a slightly different position. Oh, I know what I'll do. There we go. So what we're doing is we're just changing the x value in that initial transformation vector, and as a result, we're moving all of the translations that are based on that initial translation vector across the screen. How does this relate to what we're going to be doing?
Every time a joint moves, we're going to be doing this.
That's exactly it. Now, in this case, we're specifying a translation. When we're working with a robot, we're going to primarily be working with rotations, but it's the exact same idea. We can use this to go through and model the motion on that robot, hopefully not with this lime green color, but we can go through and define that motion relative to the origin as we move through the chain, chain of links. Good?
Didn't you say green and red was an unacceptable color combination?
Yeah, they are.
What's going on here?
I
Exactly.
don't know. It was late last night. You know, I had a glass of wine.
Someone else.
Color problems seemed mute at that point, so. Actually, it was pink and green.
Oh, yeah, it was pink.
Or was it pink and green or pink and purple?
I think it was
What?
pink and green.
Pink and green.
Yeah, okay. So this code is actually already included in the notes. So this little section you can pull out and start to play with a little bit. What I'm planning on doing for the next homework assignment is having you go through and manually calculate some displacement vectors, use your transformations, and then maybe the last three problems set up something like this where you actually map a series of translation and rotation transformations from one frame to the next. So that sound good?
I was gonna ask, the notes that you put up, the lecture notes for lecture 1, they said they were locked. I don't know if that was on purpose.
Okay, I'll have
tried
to.
putting them
Also, when I went through the quiz after I fixed the problems, it showed on my end 2 of the images as broken links. Did that happen to
On
you
the
guys?
quiz?
It did, but then it switched it automatically for me after like 2 seconds.
Okay, yeah, that's what it did for me. As soon as I refreshed the screen, it brought it back up. So just try to, if you see a broken link to an image when you're doing the chapter 1 assignment, just refresh the screen and hopefully that will resolve it for you. So, okay, so we have just a little bit of time. So let's go on through and start talking about now that we have an idea of what these translations look like, let's go ahead and take a look at least 2-dimensional rotations. And this is primarily what we're going to be interested in. You're going to see that we can in fact, we do in fact use these translation vectors, but ultimately they're only really used to describe the length of our joints. That means that they're static in nature. We hit them once, job's done. Once we do so, what we need to then do is look at the rotation of each of these segments in order to get the end effector where we want it to go. Okay, so a rotation matrix is intended to rotate an object about an origin. And let's just go through and look at a 2-dimensional object here. Let's say that we want to take that point and rotate it. What are we going to do? And just to make our life easy, we'll say that we're doing counterclockwise rotation. So we're rotating it counterclockwise to there. Why did I choose counterclockwise? Corresponds with a positive angle, right? So we're just moving it through a positive angle of rotation. Okay, so if we want to go through and rotate that, give me two ways that we can do this. We've got a vector. If we know the angle of separation, then we can just say, okay, well, we're going to go through and add the initial position to this new displacement along that angle. Now, there's a slightly different way that we can do this. Okay, so one way is just to look at it with respect to our base frame. This base frame is, we can view as non-moving. But what would happen if instead of rotating the vector, we decide to rotate the frame that it's defined in? So instead of saying that we're rotating this vector, we're rotating the entire frame that it's defined in by that alpha position. So instead of just rotating the element, we're rotating the entire universe that the element exists in. It's kind of clever, right? That's ultimately what we're doing on our robots. We're not wanting to rotate just the link within a given space. We're wanting to rotate everything that link is attached to. Therefore, everything that's attached to that link gets rotated relative to its absolute position. Okay? So we can view that rotation as changing the orientation of the coordinate system that's attached to that link. Okay? So how do we do this? Let's say that we have our base frame here, and we want to rotate it, say like this. And just for the heck of it, let's say that we have our I and j vectors. This is our I vector. This is our j vector. And I've got plenty of colors here. I actually had to open my first pack of markers today. That's amazing, so. You guys pretty much ensured that nobody in the next 5 years is getting any extra credit out of it. So what I'm doing is I'm saying, okay, well, I and j are hanging out here in our base frame. It's the universal frame. It's horizontally oriented. Our I hat prime and j hat prime are our I and j axis relative to this new rotation. So describe to me how we can describe I hat in A. Okay, well, if we wanted to, we could say that I hat prime is equal to, well, let's see, the horizontal component plus the vertical component. This horizontal component we know would be cosine of theta, because it is representing the horizontal component of the translation. So we could say that it's equal to I hat times cosine of theta. Good. And how about the vertical component? Well, this is going to be the sine component, so it's going to be plus j hat cosine of theta. So this then will be plus j hat sine of theta. And we got that done, right? That's all we need to do to rotate the I vector about an axis by alpha degrees. Oh, alpha. There's my alphas. Now, J is a little more confusing, or rather J hat prime is a little more confusing. Okay? What would J hat prime look like? How would we interpret this? Would we reference it back to the horizontal? Or is the angle we're interested in right there? We're trying to represent J in this new, or with respect to this new angle of rotation. Therefore, we would reference it back to the axis that we're looking at. Okay? So let's go through and break this down. With the angle sitting right here, what is this component? That's the cosine, right? We have the adjacent side, therefore we're looking at the cosine. So we know that we have the J hat cosine of alpha. And how about this part? This is going along our I-axis, but in the negative direction. So what would that component be referenced to? The negative sign. Okay? So we would have negative I hat sine of alpha. And we've just come up with our 2x2 rotation. Now, when we populate our rotation matrix, we have to be careful, because these are actually column vectors. So what we can say is that our rotation on a 2x2 is equal to cosine of alpha, sine of alpha, and then negative sine of alpha and cosine of alpha. How are we going to interpret this idea of rotations in 3 space? Well, if you notice here, we could say that we have a hidden third dimension here. So what axis are we rotating about if this is the xy plane? Z. So in order to perform a rotation in 3 space, what we're going to always do is choose an axis to rotate about. Okay? That's ultimately the best and safest bet. If we just try to do an arbitrary rotation and don't have something to rotate about, then everything's going to get messed up. So when we go through and define our rotation matrices in 3 space, we're going to say that Z, the rotation about Z, is going to be the cosine of alpha, sine of alpha, and no rotation influencing the axis that we're rotating about. And then negative sine of alpha, cosine of alpha, and again, no rotation about the axis we're looking at. And finally, 0, 0, 1, because the z axis is what we're rotating about. Okay. What would this look like if we were rotating about y?
You're just gonna have the zeros in that y row.
Yeah, we're just going to have the 1 hanging out right here in the middle,
Oh,
and everything else shifted accordingly. So we're going to go through and say that the rotation about y is going to have a 0, 1, 0, 0, 0. And let's see, what's going to go here? That element. Cosine of alpha. And if this element goes here, then what goes here? Negative